In episode 60, titled Fire Suppression Awareness, What Network Architects Must Account For, the goal is to treat fire suppression as both a safety requirement and an availability consideration that network architects cannot afford to ignore. Fire events are low probability but high impact, and the systems designed to suppress fire can themselves affect service continuity through shutdowns, evacuations, and equipment damage. The exam tests this topic because it sits at the intersection of physical security, facilities coordination, and resilience engineering. And it often appears as the hidden reason a redundant design still has a single-room failure mode. The right mindset is that protecting people comes first, but protecting service requires planning for what happens when alarms trigger and responders act. Architects must understand how suppression systems behave, how equipment placement affects blast radius, and how recovery works after an event. When you plan for fire suppression as a real operational condition, you reduce both risk to personnel and surprise downtime from facilities incidents. This episode builds a practical awareness model that fits what the exam expects you to know. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Common suppression types in technical spaces include gas systems and water sprinklers, and each has different implications for equipment and recovery. Gas systems, often used in data centers and critical rooms, suppress fire by displacing oxygen or interrupting combustion chemistry, allowing suppression without soaking equipment. They can protect electronics from water damage, but they typically require the area to be sealed and often trigger evacuation because breathing conditions can become unsafe. Water sprinklers are widely used because they are effective and code-driven, and they stop fires quickly, but they can cause significant equipment damage and can complicate recovery through water exposure and contamination. The exam expects you to recognize that suppression is designed for life safety and fire control, not for protecting equipment uptime. In practice, facilities may have a combination of suppression methods, and the impact of each depends on how quickly it activates and how far water or gas spreads. A network architect does not need to design the suppression system, but must design network placement and redundancy with the suppression behavior in mind. Knowing the difference helps you plan for availability outcomes when suppression triggers. Equipment placement and cable routes matter because suppression events can turn a single room incident into a large outage if critical paths are concentrated in that space. If all core switches, firewalls, and uplinks are in one room, then any suppression discharge or evacuation effectively removes the entire network core at once. Cable routes that converge through one overhead tray or one riser can also create a single point of failure because fire or water can damage multiple circuits simultaneously. Placement decisions also affect responder access because responders need clear paths and safe working space, and cluttered rooms can slow response or increase risk. The exam tests this by describing designs where physical concentration creates correlated failures, and the correct reasoning is to distribute critical components and diversify routes where feasible. Even small decisions, like not running every trunk through the same doorway or not stacking all gear in one rack line, can reduce blast radius. When you think in terms of physical failure domains, suppression becomes part of your redundancy strategy rather than an external surprise. Planning for safe shutdown and data preservation when alarms trigger is a critical operational discipline because suppression events often require immediate evacuation and controlled response. Safe shutdown means systems that can be shut down gracefully should do so when conditions indicate imminent risk, protecting data integrity and reducing the chance of corruption. Data preservation includes ensuring backups are current and accessible, and that critical configuration and state information is stored outside the affected room or facility. Alarm triggers may also cause power cutoffs in some environments, and that can cause abrupt shutdown unless uninterruptible power supplies and automation handle the transition. The exam expects you to understand that response must be predefined, because during a fire alarm, people must exit, not improvise system management in a hazardous environment. A well-planned approach includes clear criteria for when shutdown is initiated, what systems are prioritized, and how the organization confirms that data is protected. It also includes ensuring that network management access and documentation are available remotely, because physical access may be blocked. When you treat alarm triggers as operational events, you make the difference between recoverable downtime and chaotic loss. Physical separation of critical gear is one of the most effective ways to limit single-room loss, and it aligns directly with the concept of failure domains. If critical components are split across separate rooms, separate zones, or separate buildings, then a suppression discharge in one space does not automatically take down all capabilities. Separation can be achieved by distributing core network functions across multiple rooms, using redundant paths that terminate in different locations, and avoiding designs where all traffic must pass through one physical choke point. The exam often tests this by presenting a single room with all critical gear and asking what change reduces risk, and separation is the answer because it breaks correlated failure. Physical separation also supports maintenance and recovery because unaffected rooms can remain operational while one space is being cleaned or repaired. This does not eliminate the need for logical redundancy, but it ensures that logical redundancy is not defeated by shared physical exposure. When you design around room-level failure, suppression events become survivable rather than catastrophic. Access control integration matters because responders must be able to enter quickly, and delayed entry can increase damage and risk. In many facilities, network rooms and data center spaces are secured with badge access, locks, and monitored doors, which is appropriate for security but can be a problem during emergencies. Integration means there is a defined way for authorized responders and facilities teams to gain rapid access, whether through emergency access procedures, key boxes, or coordinated security protocols. The exam tests this as a balance between physical security and safety response, because a secure room that cannot be accessed during a fire event can lead to worse outcomes. Access control integration also includes ensuring that alarms and notifications reach the right people who can coordinate entry and response. Responders also need to know what is inside the space, which is why documentation and labeling matter for safety. When access is planned, response is faster, and faster response reduces damage and downtime. This is not about weakening security, but about ensuring security does not obstruct life safety and recovery. A scenario where suppression discharge forces evacuation and service impacts illustrates why availability planning must include the human response and not just equipment survival. If a gas suppression system discharges, personnel must evacuate and may be prohibited from re-entering until the area is declared safe, which can delay manual interventions. Even if equipment continues running initially, the event may trigger shutdown procedures, power cutoffs, or network isolation depending on facility policy. If water sprinklers discharge, equipment may fail immediately or shortly afterward, and cleanup can take days, making service impacts long-lasting. During such events, service continuity depends on whether critical services can fail over to other locations without human presence in the affected room. The exam often expects you to recognize that evacuation is part of the failure because it removes the ability to perform local recovery quickly. A design that assumes staff can walk into the room and fix things during an alarm is not realistic. When you account for evacuation and restricted access, you naturally prioritize remote management, automation, and geographic redundancy. A dangerous pitfall is storing flammable materials in network rooms, which increases fire risk and can worsen suppression outcomes. Network rooms sometimes accumulate cardboard boxes, packaging, spare cables, cleaning supplies, and other materials that are not meant to be stored there, and these materials can fuel fires or obstruct airflow and access. Flammables also increase smoke production and contamination, which can damage equipment even if flames are contained quickly. The exam tests this because it is a straightforward physical security and safety principle, and because it directly affects availability through increased fire probability and severity. A room designed for critical infrastructure should be treated as a controlled environment, not as a general storage area. Reducing combustibles reduces the chance of ignition and reduces the intensity of a fire if one starts. It also improves responder access and reduces cleanup complexity after an incident. When you manage the space properly, you reduce risk at the source rather than relying solely on suppression systems. Another pitfall is lacking documentation for responders and facilities teams, which slows response, increases confusion, and prolongs downtime. Responders need to know what equipment is present, where critical shutoffs are, what hazards exist, and how to contact responsible personnel. Facilities teams need maps, labels, and clear indications of which racks support which services so that recovery and cleanup can be prioritized correctly. Without documentation, teams may waste critical time identifying what is safe to touch, what can be powered down, and what must be preserved. The exam expects you to recognize documentation as part of resilience because it affects recovery speed and accuracy. Documentation also supports post-event restoration because you can rebuild configurations, reroute circuits, and reestablish connectivity faster when you know what was there. In a high-stress event, undocumented systems become unmanageable systems. When you maintain clear documentation, you reduce the operational chaos that turns a facilities incident into a prolonged outage. Quick wins include maintaining maps, labels, and emergency contacts posted so that both responders and internal teams can act quickly and safely. Maps should show rack layouts, critical path cabling, and where key devices and shutoffs are located, and they should be kept current as changes occur. Labels should clearly identify circuits, PDUs, uplinks, and critical devices, reducing guesswork during recovery. Emergency contacts should be visible and accurate, ensuring the right people are reached during off hours when incidents often occur. These quick wins are effective because they do not require major capital investment, yet they dramatically reduce response time and recovery errors. The exam often rewards answers that emphasize preparation and clarity because they reflect real operational resilience. Posting contacts and maps also supports compliance and safety audits because it demonstrates that the organization has planned for emergencies. When documentation is visible and actionable, the facility becomes easier to operate during crises. Recovery planning must also account for smoke damage and contamination cleanup, because many outages are extended not by fire itself, but by what fire leaves behind. Smoke residue can be corrosive, and particulate contamination can clog fans, coat boards, and reduce insulation, leading to failures weeks after the event if equipment is returned to service without proper cleaning. Water events can introduce moisture into equipment and cabling, requiring drying, replacement, and sometimes complete rebuild of affected sections. Cleanup must be done safely and often requires specialized remediation, which means the room may be unavailable for an extended period. The exam expects you to recognize that recovery is more than powering equipment back on, because contaminated equipment can fail unpredictably and can cause repeated incidents. A good recovery plan includes criteria for what equipment can be salvaged, what must be replaced, and how to validate stability before returning to production. It also includes preserving evidence for incident investigation if the event involves safety or insurance processes. When you plan for cleanup and validation, you reduce the chance of recurring failures after the initial event. A useful memory anchor is protect people, protect gear, plan recovery, because it keeps priorities and actions in the right order. Protect people reminds you that life safety is the top priority and that evacuation and responder access must be enabled rather than obstructed. Protect gear reminds you that placement, route diversity, and controlled environments reduce the chance a single event destroys all critical equipment. Plan recovery reminds you that suppression events can produce long restoration timelines due to smoke, water, and restricted access, and that documentation and remote failover capabilities determine how long service is impacted. This anchor helps you answer exam questions because it connects safety, architecture, and operations in a coherent way. It also prevents the mistake of focusing only on hardware survival while ignoring human and procedural realities. When you can explain the anchor, you can explain why a design is resilient to fire events beyond simply having extinguishers and alarms. To apply the concept, imagine being asked to list 3 design choices that reduce fire risk impact in a facility that hosts critical network infrastructure. You would choose physical separation of critical gear across rooms or zones so a single suppression discharge does not remove all connectivity. You would choose diverse cable routes that avoid single trays or risers so physical damage does not sever every critical link at once. You would choose a documented alarm response plan that includes safe shutdown and data preservation behavior supported by remote management and clear maps for responders. You could also emphasize keeping network rooms free of combustibles and ensuring access control supports emergency entry because these choices reduce both fire probability and recovery time. The exam expects you to connect design choices to reduced blast radius and faster recovery rather than to generic safety statements. When you can justify each choice by explaining what failure it prevents, you show the reasoning skill being tested. Fire resilience is about reducing correlated loss and enabling safe, rapid response. To close episode 60, titled Fire Suppression Awareness, What Network Architects Must Account For, the essential point is that fire suppression affects availability and must be accounted for through placement, route diversity, operational planning, and recovery readiness. Gas systems and water sprinklers have different failure implications, but both can force evacuation and restrict access, which means continuity depends on redundancy outside the affected room. Equipment placement and cable routing determine whether a suppression event becomes a localized incident or a site-wide outage, and physical separation of critical gear limits the impact of single-room loss. Safe shutdown and data preservation planning ensure that alarms trigger controlled behavior rather than chaotic loss, while access control integration ensures responders can enter quickly without security barriers slowing life safety response. Avoidable hazards like flammable storage and missing documentation increase both risk and downtime, while quick wins like maps, labels, and posted emergency contacts improve response and recovery speed. Recovery planning must consider smoke damage and contamination because cleanup and validation often dominate restoration time. Your rehearsal assignment is a facility walkthrough narration where you describe step by step how a critical room is laid out, where redundancy exists, how responders would gain access, and what the shutdown and recovery plan would be, because that narration is how you turn fire suppression awareness into practical architectural resilience. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.